Welcome to the lecture An Introduction to Large Deviations. Today we will talk about uniqueness of rate function for in large deviations. Let me write the topic. It is the next topic is lower semi-continuity. Continuity and goodness of a rate function. And section 5.1, lower semi-continuity of rate function. Lower. And here I would like to start my lecture with the following question. Assume you have a family of random elements in some metric space that satisfies the large deviation principle with some rate function I. And the question is this rate function unique, or probably there could exist another function, say I tilde, such that this family satisfies the large deviation principle associated with that another rate function. And the answer is here, no, it is not the case. If you don't assume any additional assumptions or any additional properties on the rate function. Then I want to start here from the following example. 5.1. And let's take that random variable xi that has a normal distribution with mean 0 and variance 1. And define the family of random variables psi epsilon that is square root epsilon xi. And we know that this family, we know that psi epsilon satisfies the large deviation principle with rate function I of x that is equal to x squared divided by 2. What does it mean? It means the following, that for last time we discussed two equivalent formulation or definitions of large deviation principle. One was given as a definition, another was given as a statement of the lemma, but last time we discussed that these definitions are equivalent. So very often I will work with some of them like as a definition. Therefore here, just to recall what it means, we will use the statement of the lemma. It means here that for every f closed, you have that. We need more space. You have that upper limit, epsilon goes to 0, epsilon logarithm, the probability psi epsilon belongs to f is less or equal than minus infimum over f of the function I. And for every g open, we have that lower limit, epsilon logarithm, the probability that psi epsilon belongs to the open set G is larger or equal than minus infimum G of I. And now I want to a little bit spoil this function. I want to take the function I tilde of x that is defined as follows. It is x squared divided by 2 when x is not 0, and then I take plus infinity when x is equal to 0. And then our goal is, in this example, show that psi epsilon satisfies the large deviation principle with rate function I tilde. And why it is so? Well, indeed, if let's start the discussion from that case. So therefore, you want to show that type of inequalities, but when you have here tildes, and we start from that case that or that inequality that in this case is simpler. If G is open, then you have that, I would say that it is trivial, that I over G is equal to infimum of I tilde over G. And here the reason is that if 0 point does not belong to the set G, then these two functions coincide. Therefore, the infimum also must be the same. But if it happens that 0 belongs to the open set G, then also since G is open, it belongs with some neighborhood. So therefore, anyway, you need to compute the infimum over that, particularly over that neighborhood, and therefore this plus infinity will not play any role when you compute the infimum. Therefore, these two infimums must be the same, and since they are the same, then you have the large deviation principle with rate function I, so therefore you also have this estimate with the rate function I tilde. The second estimate is that if f is closed and such that f is not identical is not 0 point, it has also some other points except 0, then you have that also because of the same reason infimum of I over f is equal to infimum of f I tilde. Because when you start computing infimum, you will need to consider only the values of function I of f for all x that or for x that belongs to f except the point 0. And these two functions coincide. Therefore, infimums also must coincide. Only that everything what you need to check or care about, it is the case if f is equal to only 0 point. This set also is closed. And here we need to just make the computation. Epsilon logarithm the probability that psi epsilon belongs to f. It is the limit epsilon goes to 0 that epsilon logarithm the probability that psi epsilon is equal to 0. But you see that random variable psi epsilon has normal distribution. It has a density, and we know that the probability that random variable with density is equal to some point, it is equal to 0. Therefore, that part is equal to 0. Logarithm of 0, according to our agreement, is minus infinity multiplied by epsilon also minus infinity. Therefore, this is minus infinity, and it is exactly minus infimum of I tilde over the set f. That is 0 point, because you see that here you have I tilde is plus infinity. So we came to the conclusion that psi epsilon satisfies the LDP with I tilde. And then the natural question is, can we we can we um, impose some additional conditions on the rate function I to have uniqueness. And today we will answer that question. And you will see that this additional condition or additional assumption is the lower semi-continuity. We will show that if the rate function is that there exists a unique lower semi-continuous function associated with large deviation principle for given a family of random variables. And we need to write the definition. What means that the function is lower semi-continuous? A function f from the metric space E, where we consider our family of random elements or variables, to say minus infimum plus infimum, let's give the definition in general case, is called lower semi-continuous, I'm sorry, so lower semi-continuous. If one has that the lower limit n goes to infinity, fx epsilon larger or equal than f of x whenever xn converges to x. And we should remark here that each continuous function, oh, I'm sorry, here should be, it is a typo, here should be n. Each continuous function is lower semi-continuous. And also, let's note that because of this, in particular, in this remark, that the function I of x that is equal to x squared divided by 2 is lower semi-continuous. But the function that was on the previous slide, that function is not lower semi-continuous, is not. Not lower semi-continuous because since if you take the sequence xn that is equal to 1 over n that goes to 0, you see that the lower limit n goes to infinity of I tilde of x or 1 over n. It is a limit n goes to infinity 1 over 2n square, and this is 0, but this is not larger or equal than the function I tilde of 0 that is equal to plus infinity. It is not. That means that the function is not lower semi-continuous. There is another characterization of lower semi-continuous function that also is that allows you to work with that type of functions in some cases easier, and that we will formulate as a lemma. 5.4 that a function f from the metric space E to minus infinity plus infinity is lower semi-continuous if and only if for each alpha from minus infinity to plus infinity, the set or the level set that um, all x from E such that f of x is less or equal than alpha is a closed set. Let's specify here in of some picture. You have some function f, for instance, that function looks like that. And then you take the level alpha, yeah. But maybe it would be better to take alpha a little bit below to have a more interesting picture. Then the lower set, it is all x where the function is below the level alpha or equal alpha. Thus here in this picture, the level set it is z set union with z set. And then the statement say if that set is closed, then the function is lower semi-continuous, and also the inverse statement also is true. And by the way, if you consider the level set for IT, you also will see that the set is not closed because each level set for every alpha, it will not contain the point 0. If alpha is if alpha is positive, then it will contain all points around 0 except the point 0, which tells that, or which simply implies that the level set for this function is not a closed set. Now we want to prove that that statement. And here we have to prove in both directions. Assume that f is lower semi-continuous. And we take alpha from minus infinity to plus infinity and set for alpha set the level set or denote the level set by L alpha. It is x from E such that fx is less or equal than alpha. Sometimes we will write that shorter. We will just write f is less or equal than alpha. If alpha is equal to plus infinity, then trivially the level set is the complete space and it is closed. And now assume that alpha is smaller than plus infinity. And then we need to show that the level set is closed. Also assume that it is not the case. That and alpha is not closed. And we want to get a contradiction with that assumption. If L alpha is not closed, then it implies that there exists a sequence from the level set such that this sequence converge to some point x and I'm sorry, I didn't say that xn belongs, not, I said that xn, so there exists a sequence from L alpha, which converges to x, and this alpha x does not belong to n, to L alpha. And now using the definition of lower semi-continuity, we get that f of x is less or equal than the lower limit n goes to infinity of f of xn. But let's remark that x belongs to L alpha, and it is below. It means that the value of function f at xn is less or equal than alpha, and this is also so for the limit. Then the right hand side is less or equal than alpha. But x here does not belong to the level set. That it means that that the function f does not satisfy that property at the point x, then it must be larger than alpha. And then you get the contradiction, because from one side you got that alpha is strictly smaller than alpha. Contradiction. In another direction, let's assume that L alpha is closed for every alpha from minus infinity to plus infinity. And also assume that that f is not lower semi-continuous. Then then we want to get the contradiction with this assumption. If the function f is not lower semi-continuous, then it means that the definition of lower semi-continuity is not satisfied, and this implies that there exists a sequence xn which converges to x, but that the lower limit f of xn n goes to plus infinity is smaller than f of x. And now we take alpha that is between the lower limit and the value of f at point x, such that the lower limit is less than alpha and less than f of x. And since the lower limit of the sequence of that sequence is less than alpha, then by the definition of lower limit and the assumption that the lower limit is less than alpha, we can find or they exist a subsequence x and k of the sequence xn such that it is the limit of f of x and k is exactly the lower limit. It follows from the fact that the lower limit is the smallest smallest limit point of that sequence. K to plus infinity. And of course, this is less than alpha. And also, we can start from k so large that that not only the limit is smaller than alpha, but also that functions also will be smaller than alpha. So therefore, without loss of generality, we also can assume that f and k is less than alpha. So then this implies, in particular, that the x and k belongs to the level set L alpha. And also, since x and converge to x, then x and k also converge to x. So then this must imply that x belongs to L alpha since L alpha is closer. And now we get the contradiction because that implies since x belongs to the level set, it implies that f of x is less or equal than alpha. But you see that here we have that f of x is larger than alpha. That gives us the contradiction. Maybe somehow I can put I can write that part, this one line here. So then this implies that f of x is less or equal than alpha, and then I want to mark that our conclusion with that part that contradicts each other. This gives the proof of the statement. And now we can use these two assumptions, like the definition and the statement of the and of the lemma, without any further discussion, when we want to prove that some function is a lower semi-continuous function. Now let's consider some additional examples of lower semi-continuous function. We already said that each continuous function is lower semi-continuous function, but now let's consider another non-trivial example of the function which is not continuous but lower semi-continuous, and we will work not with the space R or RD, but with infinite dimensional Banach space. That example. Now I want to consider the space of continuous functions, which I denote C00T. It is the space, the Banach space of continuous functions. F from 0t to R, such that f of 0 is equal to 0. Actually, this 0 here, it means that the function at point 0 is 0, or if you consider f as path of some process, it means that f starts from 0 at time 0. And we equip this space with a uniform norm. And so the space 0t with uniform norm that is the norm, say, I will put here infinity. It is the maximum or supremum. T belongs to 0 capital T, absolute value of f of let me write that of f of t Okay. And you know that this space is a Banach space. It is a complete separable normed space. Then to define the function I, which also will appear later as some rate function for some family of stochastic processes, we introduce also a subset of this space at h0 to 0 here, be the set of all absolutely continuous, of all absolutely continuous functions f. So from the space C0, 0t, this is a subset with so the derivative or generalized derivative that belongs to that is square integrable with respect to Lebesgue measure. Let's here note that f is absolutely continuous if it can be written as also you see that the function here we work with functions that start at 0, so therefore we will have here like 0, or maybe it makes sense to write that completely. Okay, just some function is absolutely continuous if we can write it in the following form. And this sum function f dot, it is some function such that you have that expression where f dot is some function. So that is integrable, some integrable function. You can easily show that this function is almost surely unique. If there is another function for which you have that expression for every t, sorry, here I didn't write that, for every t, then that two functions inside integral must be almost surely unique, or must coincide almost surely. Sorry. And then we consider, once again, we consider this. It is a set of absolutely continuous functions or functions that can be written in this form with some function that is integrable with square, such that the integral of f dot square is finite for every t. And for this function, we define for that we defined that the map I, it is plus infinity if the function f does not belong to h0 to 0 capital T, and 1 over 2 the integral from 0 to t f dot square of t dt. Now note that this integral is finite in the case when f belongs to that set. If f belongs to 0 to if you know what the Sobolev space is, then this is like W12 Sobolev space. But still, you don't need to refer to Sobolev spaces because you can here operate with absolutely semi-continuity, absolutely continuity of functions, and then you can clearly like work with that type of definition to prove something, to in particular to prove that this function. So then let's write that as an exercise show that the function I is as a function from the space C0, 0 capital T to 0 plus infinity is lower semi-continuous. This function, it will be later, we will show that this function, it will be the rate function for the family of Brownian motions. Okay, good. Then our goal will be to show that if you have the large deviation principle with some rate function that is not necessarily lower semi-continuous, that you can always build another function that is lower semi-continuous, and it is also the rate function for the given large deviation principle. And to build such a function, we will need to do some type of lower semi-continuous regularization. And let's define it here. Okay, we define the lower semi-continuous regularization. Let me start this from the new slide. Of the function f from the metric space E to minus infinity plus infinity. And we define that regularization as follows. We will denote that by f lower semi-continuous regularization of x. It is given as follows. You compute, first of all, you fix the point x. Then you take an open set which contains x, and G is open. And then you compute infimum of f over that set G. And then you take supremum over all sets such set G. Once again, you take supremum over all sets, over all open sets, which contains the point x of the infimum of the function f over the set G. Example. Let's take the function I tilde, which we already considered, and it was the function x squared divided by 2 for x is not 0, and then plus infinity when x is equal to 0. And let's try to find the lower semi-continuous regularization for that function. Yeah, too sloppy. It is the picture. The graph of function looks like parabola. But at the point 0, it is equal to plus infinity. It is equal to plus infinity. Okay. And then when you compute the lower semi-continuous regularization, say at this point x, then this point I tilde of x, maybe I wrote x by green point. Let's also write that here. What it is, again, you need to take supremum you need to take infimum, it is lower semi-continuous. You need to take infimum of the function I tilde of y, and y belongs to G. Oh, therefore, what you do here, you just fix it any open set, say a ball or an interval, an interval, and then you compute the smallest number of the function on this interval. But after that, when you computed it, and for that set G, the smallest number, it will be here. It is infimum. But then you need to take supremum over all possible open sets that contains X. And here you see that, that the supremum or the maximal value, which actually you can get here, it is in the case when this set becomes like smaller and smaller. And then the supremum will exactly go to the value of the point I tilde of x, that is x squared divided by 2. It is infimum over all g from x, such that g is open. And this is x squared divided by 2. But if you take x that is here, then I tilde lower semi-continuous regularization of x in this case, now x is equal to 0. Again, you need to compute the infimum over the open set which contains x, and you see that always that infimum will gives you something, will gives you always 0. All right, because if you take an open set G, then it contains some neighborhood of X that is, for instance, interval, but infimum over that interval it is 0. So therefore, supremum also is equal to 0. So then you came to the fact that I tilde of X lower semi-continuous, it is X squared divided by 2, because it is 0 squared divided by 2 for all X. Good. I hope that more or less intuitively it is clear for you what is the lower semi-continuous regularization, or how we can, or how actually we work with this type of definition. Later, I will also formulate an equivalent definition of lower semi-continuous regularization that includes or where we will use sequences, but not open sets. And now the next lemma says that will be about some properties of lower semi-continuous regularization. In particular, now we will formulate and prove that the lower semi-continuous regularization, it is a maximal lower semi-continuous function that is less or equal than the function f. Lemma. In the lecture notes, it is 5.10. The function f lower semi-continuous regularization, that function is lower semi-continuous and it is smaller than the function f for every x. If g is another lower semi-continuous function, is lower function and satisfies or it is smaller or equal than f, So once again, so this function is the lower semi-continuous and it satisfies that property. But if you take another function that satisfies the same property, then G is smaller or equal than F lower semi-continuous regularization function of F. So in particular, F is lower semi-continuous, then this regularization is exactly the function. So that construction here does nothing with the function f. Okay, and now we want to prove that statement, since it will be exactly the way how we will build the rate function or lower semi-continuous rate function associated with some large deviation principle for a function for the rate function that is not lower semi-continuous. Our idea will be, we will consider function I that is not lower semi-continuous. We will apply this lemma. We will get the lower semi-continuous function using this type of regularization. And then our goal will be to show that with this new function, you also have the large deviation. But before, we need to prove that lemma. First of all, I want to note that the inequality of f lower semi-continuous is less or equal f is clear. Since infimum over g of the function f is always less or equal than f of x for every g that contains the point x, because I mean, in particular, x also is in the set G, therefore infimum can be only smaller than the value of function f of x. And now when you take supremum, this also over all sets that satisfies that property, also you cannot get something larger than the function f of x. That gives the proof. Now we want to show that the function is lower semi-continuous. Show that is lower semi-continuous. And for that, we will use the claim that it is lower semi-continuous if and only if the level sets are closed set. We need to show that the level sets f lower semi-continuous less or equal than alpha is closed that for each alpha. But this is equivalent to the claim that the complement that is the values of functions or arguments of functions where it is larger than alpha is open. So therefore, we fix alpha, and we want to show that this set here is an open set. And to do that, we need to show that every point has an open neighborhood which is a subset of the complement of the level set, of this set here. So we take X from that set and find an open neighborhood of X such that, let's denote it by G, such that of X such that this G also is subset of F lower semi-continuous. That it exactly means that the set is open set. We we note that F lower semi-continuous of X is larger than alpha because X belongs to that set, and it means that X satisfies that property. That X satisfies that property here, and but this the value of that function, it is the supremum over the set X that are neighborhoods of points X and are open of such infimums. So, and now you have that supremum is larger than alpha, and it means that they exist at least one set, one open set G containing X, such that this infimum is larger than alpha. This implies that there exists G open such that infimum, so first of all, F lower semi-continuous X is larger or equal than infimum of G of the function F, and it is larger than alpha. Okay, then let's go further, and now we show that G is a subset of this complement of the level set that we consider. F semi-continuous is larger than alpha. To show that, what we need to do, we need to take an arbitrary point G and satisfy that for that point, the value of function of this function also is larger than alpha. Why? Then you have that F lower semi-continuous of the point Y, and let's compare this with the infimum of the function F over G. You see, you took Y from G, so therefore it is like an open neighborhood of this point Y. But the value of that function, it is a supremum over all G that are open and contains Y. But this is a fixed G that contains Y. Therefore, the supremum can be only larger or equal than the infimum. But on the other side, we said that, or we choose this function, the set G by such a way that the infimum is larger than alpha. And it implies that Y belongs to F lower semi-continuous larger than alpha. That implies that G is a subset of F lower semi-continuous larger than alpha. That implies that this set, I'm sorry, here F is open. And that implies that the function F lower semi-continuous is lower semi-continuous. Okay, we already proved the fact that F is lower semi-continuous, and also this inequality. Now it remains to show that if you take a lower semi-continuous function that is smaller or equal than the given function f, then also it is smaller than equal than its lower semi-continuous regularization. And to show that, G is less or equal than f lower semi-continuous, we need to show that its lower semi-continuous regularization is equal to the function g. You remember that function g is lower semi-continuous, and if we show that its lower semi-continuous regularization is exactly the function g, then we will obtain this statement, because if you take the function g and if you write and if you know that it is equal to the lower semi-continuous regularization, but this is supremum of infimums of the function g over the set capital G that is x, that contains the point x, and g is open. But now, according to our assumption, this function is less or equal than the function f. So therefore, if in this infimum you replace the function g by the function f, you will get something larger or equal. So therefore, the supremum also will be larger than equal. But it is exactly f lower semi-continuous regularization. And then you will get the inequality. Oh, therefore, we will focus on the proof of this. First of all, we note that g lower semi-continuous regularization is less or equal than the function g. We prove that for the function f here, or we discussed that here, but now we have the function g, so therefore you also have the same inequality. Then we need to prove the inverse inequality. It is that what we want to prove. And to show the inequality in this direction, let's use the following trick. Let's take just an arbitrary alpha such that g of x is larger than alpha. And consider the set g that is equal to g larger than alpha. You remember that the function g is lower semi-continuous, and this function that we consider here, it is a complement to the level set. So therefore, this set is open because g is lower semi-continuous. And also, this set x, the set g belongs x, right? Because when you plug in here x, you will have that inequality according to the choice of alpha. So therefore, this set which we took here, it is one of the sets in this supremum. And also it is one set of that supremum. And also let's note that that if we take the infimum over the set G of the function G. So if you take any point satisfying this inequality and then you compute infimum over such a points of the values of function G, you see that it is larger or equal than alpha. And since, as we said, that G, it is one of the sets here, then the supremum must be larger than this particular infimum. That implies that that supremum of the infimum over now any arbitrary G is such that X belongs to G and G open also must be larger or equal than alpha. But this supremum, it is the lower semi-continuous regularization of the function G. Thus, continuous X is larger or equal than alpha for each alpha satisfying that are smaller than G of X. But now let alpha converges to G of X. So it just increases to the value of function G of X. And for all alpha, you have that inequality. When you pass to the limit, also the inequality is preserved. Then it implies that G lower semi-continuous regularization is larger or equal than G of X. That gives the proof of the lemma. And now to finish the discussion of lower semi-continuous regularizations, I would like to formulate an exercise which also will give us an alternative definition of lower semi-continuous regularization, and then probably it will be later easier for us to work with it. It is exercise 5.11 in the lecture notes. And the first part, it is actually not very useful for us, but let's formulate it. Show that that if xn goes to x, then f lower semi-continuous regularization of point x is less or equal than limit n goes to infinity f of xn. The second part is show that that actually the supremum can be taken. You don't need to consider in the definition of lower semi-continuous regularization over all open sets that contains X. It is enough to consider the supremum only on the, over the balls with the center at the point X. This regularization can be defined also f the supremum, but now over all possible radiuses of the balls infimum y belongs to the ball radius r with the center x of f of y. And the third part is that proves that for every x from E with xn converge to x. I'm sorry. For every x, there exists a sequence xn such that xn converge to x and f of xn converge to f lower semi-continuous regularization of x, and this gives the alternative definition. It is namely that f lower semi-continuous regularization, it is just minimum. Either it is the value of function f itself, or it is a lower limit over all sequences that converge to x of the function f of y. Just taking into account that this this property here, you can also, I'm sure that you can also get like more or less good intuition what is a lower semi-continuous regularization. Actually, you take a bad points where the function f is discontinuous, and you move these bad points down to the main graph of the function f. Of like in this example, you see that when you had the function I tilde, what we did with that point, and also now we can use this alternative definition, you just need to consider all possible limits to of the function f to when argument goes to the point x, and these limits will converge to 0. And then you need to take the minimal one that is also 0. And it gives you exactly the lower semi-continuous regularization that is that point. For instance, you can immediately answer the question when I draw two graphs. And for instance, one graph, it is like that graph. And here you have the value of function is somewhere here. Or I will take the graph of function that looks the same, but then the point, its value at that point, it is negative, then you can immediately say that, okay, this function here is lower semi-continuous, but this function is not lower semi-continuous. And to get the lower semi-continuous regularization, you just need to take this point and move it down to the main part of the graph. It is very roughly, of course, but at least maybe this will help you to better understand what the lower semi-continuous regularization does, at least in the case when function is defined on, say, on R or on RD. Okay, and now we are ready to prove the main statement of this lecture, namely that we always have a large deviation principle with the rate function that is lower semi-continuous. We know how we can build that lower semi-continuous function, and also we will claim that this lower semi-continuous function is unique. Then proposition 512. Let psi epsilon epsilon larger than 0 satisfy the large deviation principle in a metric space E with a rate function I. Then it satisfies the large deviation principle in E with the rate function I lower semi-continuous regularization. Moreover, there exist only unique lower semi-continuous associated rate function. Okay, now we want to prove that proposition. And we will start first of all with the proof of the fact that we also have large deviation principle associated with that function. First of all, we want to note that the I lower semi-continuous is less or equal than I. We have that it follows from the previous lemma. And in particular, this implies that for every f that is closed, that for every f closed, you have that the upper limit epsilon goes to uh, to 0, epsilon logarithm the probability the probability that psi epsilon is less or is belongs to f is less or equal than minus infimum over f I. It is exactly like a part of definition of large deviation principle. But now you see that this you have this inequality. Therefore, with minus, you will have the inequality in that direction. Then you can continue and write here less or equal than minus, and then replace the function I by this regularization. That immediately, like for free, implies the upper bound for large deviation principle. Now we need to prove the lower bound. We need to prove. Then for every G open, we want to show that lim epsilon goes to 0. Epsilon logarithm, the probability that psi epsilon belongs to G is less or equal than minus infimum over G. I'm sorry, it is larger or equal than infimum of I lower semi-continuous. It is a question. It is what we want to prove. But we know that it is larger or equal than minus infimum I over I because it is definition. So say like definition of large deviation principle. Oh, therefore, here idea to show the inequality for this function. Everything what we will do, we will show the equality between two infimums. We show that infimum over G of I lower semi-continuous is equal to infimum of I over G. And this will finish the proof of the first part of the proposition for G open. First of all, we note that infimum G I lower semi-continuous less or equal than infimum I of G, and this follows from that. Then we need also to show that in another direction. Then in order to prove the inverse inequality, we will use the definition of lower semi-continuous regularization. So we remark that so note that for x, for each x from G, you have that f lower semi-continuous, oh, I'm sorry, I lower semi-continuous regularization is larger or equal than infimum over gi. Again, because this function here, it is supremum of all infimums over the set G that is open and contains the point X. So therefore, the supremum must be larger or equal than one particular infimum. And that is for every X from G. So therefore, this implies that also infimum of I lower semi-continuous of X over G is larger or equal than infimum of I over G, because it is satisfied. I mean, that point is satisfied, that inequality is satisfied for every X from G, so then for the infimum. And this proves the first part of this proposition, that you have also large deviation principle with the rate function that is lower semi-continuous regularization. Now we want to prove that the lower semi-continuous regularization is unique. And to prove the uniqueness, we assume that we have two rate functions which are lower semi-continuous, and our goal will be to show that these two functions are the same. So we assume that psi epsilon satisfies the large deviation principle with I and j, with both rate function, and I comma j are lower semi-continuous. And our goal is to show that they are the same, but now let's assume that it is not. So let I is not j. So it implies that there exist x from E such that I of x is less than j of x, or j of x is less than I of x. And of course, it is clear that it is enough to consider only one case, this case, because that case is similar. You just need to interchange both functions. So therefore, let's focus on that part. Without a loss of generality, assume I of x is less than j of x. And now we want to obtain the contradiction. Let's use just using the lower semi-continuity by the lower semi-continuity of G. We may choose a neighborhood G of x. That means that x belongs to G and G is open, such that infimum over G closure of J is larger than I of x. Taking, for instance, the open set G as an open neighborhood of x such that G closure is a subset of the level set of Y j of y larger or than I of x plus j of x minus I of x divided by 2. I want to know that since that function is lower semi-continuous, this set is open, therefore, and also trivially the point x belongs to that set. And because when you put here x, you will come to the inequality that I mean, because of that inequality, you can conclude immediately that one. And also, since that this set is open, you can always choose an open set that also belongs here, and then you can make it a little bit smaller, such that the closure also will be there. For instance, you can work with balls. You can take balls and make it like take a half of ball, and then therefore the closure of this half of ball will be in larger ball that is a subset of this set. And now we can get immediately the contradiction, because then with this choice of G, we have that minus I of x that is less or equal than minus infimum of I over set G, because G contains x, therefore infimum must be smaller, but minus infimum larger, is less or equal than, and here we use large deviation principle, is less or equal than lower limit of epsilon logarithm the probability that psi epsilon belongs to G. But you know that it is larger or equal than the upper limit, according to the definition. And in the definition, this upper limit is larger or equal than minus infimum. But now you also have that this family satisfies the large deviation principle associated with G. So therefore, you can use here the function G. And now you take G closure. But you see, you choose that set G closure such that this infimum is larger than I of x. So therefore, minus infimum is smaller than minus x. And you can continue the estimate and can say that it is smaller than minus I of x. And you get the contradiction, because here, because you started with minus I of x, you got minus I of x, and somewhere between you got like the sign strictly smaller. Then, of course, give the contradiction. Okay, it is almost everything for today. Today we discussed the uniqueness of rate function in the case if it is lower semi-continuous. So therefore, later when we formulate large deviation principle, it always makes sense to write large deviation principle with lower semi-continuous rate function. Because it has some additional regularity, it has some additional structure, and then it can be a useful property for our goals. But sometimes you also can expect that your function is not lower semi-continuous. It is even better. And let me finish this lecture with one definition that is called goodness, or what means that the function is good. And also later you will see that usually in the examples of large deviations that we have, the function will not be only lower semi-continuous, but also it will be a good rate function. And what does it mean that the function is good? It is the following. So it is 5.2, goodness of rate function. And we just write the definition and only example, and it will be everything for today. The definition 5.14, we say that that a rate function I from metric space E to 0 plus infinity is good if the level set x from E such that I of x is less or equal alpha are compact. Rather than just closed for all alpha that are not negative. Oh, you see that the lower semi-continuity or lower semi-continuity is equivalent to the fact that sets are closed, but now we assume a little bit more. Then they are not only closed, but also they are compact. So therefore, every good function, it is lower semi-continuous, but not each lower semi-continuous function is a good rate function. And examples. Yes. So for instance, the function I of x, that is x squared divided by 2 here, E is R, or that function that we also defined today as an example of the function of the function rate function for the Brownian motion, that is plus infinity when f does not belong to h0 0t, and 1 over 2 integral from 0 to t f dot square of t dt, and f belongs to h0 square 0t r. And here that space E is equal to C0 0t are good rate functions. And that we will leave as an exercises. For you, you will get that for as an homework exercise to show that. Okay, it is everything for today. Thank you so much for your attention.